For example, if the ith server is busy, you try to assign that to i+1 server and so on. So you are giving strictly increasing array arrival of positive integers where arrival represent the arrival time of ith request and other array reload where where the load I represent the load of the ith request, the time it takes to complete. Your goal is to find the busiest server actually. Okay. So a server is considered to be busiest if it handled the most number of requests successfully among all the server. Great. So if you look at this question, I feel like this question is similar to scheduling task. I don't think this is very commonly asked. It's probably asked to a couple of people, like who has experience on handling jobs, on servers or CPUs or something actually. And also this is a combination of problems. Similar problems we have seen scheduling meeting, like meeting intervals, merge intervals. So these are all combinations of that problem. If you have answered those questions, it probably easier for to do that. Let me look at that problem. So how do we see that actually? How can we do that? The input is given. If you look at the input is given like this. K is the number of servers, which is 3. It has an arrival time. Basically, this is the start time of that particular job. 1, 2, 3, 4, 5. And the load is like so how long it needs to be run actually, on this particular server. Is probably the first server is arriving at 5 and it takes, maybe if you say that 5 milliseconds or something, so it will be 1 plus 5 the total time which is required. Start from 1 and 5, that means the server is free after 6th millisecond, if I assume that the load is given in milliseconds actually. And you can see that, and the next is 2 and 3, 3, 3. And you can see that in the figure, you can see that they have given the first 3 requests are handled by first 3 servers. So basically it indicates R0 first load, R1 is a second load, and R2 is a third load, and 4th, 5th, something like that. So you can see that here first 3 is handled. So basically server 0 handled the first load, which is 5, then it will goes to R1 load 2, then R2 load 3, and after that the third load comes. They look at it which is free basically. Server 0 is busy, so it's assigned to the next available server. So the servers are defined by I modulo k. So I will explain you how that needs to be done. So that's the reason when the third request come, so I modulo k is literally it is the 4th load, and in index we say 3 by k is the total number of servers available, so which will be 0. So it is trying to assign to the 0th server, but since it is busy, it went to next server. You see that the next server is server 1, and the server 1 job is finishing in 4, 2 plus 2, 4, and the next job, oh sorry, yeah, so this one, 2 plus 2, 4, and the job which is come is 4, 4 plus 3 7, and the start time of that job is 4, and basically the whatever the server 1 is handled, the job is already over. That's the reason the index third job, basically the fourth job is handled in server 1 actually. When the fourth job comes, basically the request 4, basically it's a request start from 0, so that's the reason the fifth request, basically the R4, it cannot be handled, so all the servers are busy, so it is dropped actually. And when you look at it, the server 1 handled the 2 loads, so that's the reason we are returning R1 actually, sorry, the R1, the total number of servers handled R1 and R3, so that's the reason we are returning the server 1 actually. Okay, so how do we solve this problem? Whenever we see this kind of problem, and you see that they are given in a sorted order in both, so that means we don't need to sort anything. That's already mentioned, the requests are coming in the question itself. They mentioned actually requests are coming in sorted orders actually somewhere, yeah. Okay, so basically what we need to do is actually, if you look at it, we need to assign jobs, since it has 3 jobs, basically assigning the meeting rooms. If you look at it, meeting room, and there is a meeting is scheduled, and when the next meeting is coming, we need to check whether the meeting is over or not, or it will end at the same time. Similarly, we need to do that actually here. If you look at it, the first job starts at, if you draw a line, and you can see that we can make something like this, which is a time, and this is the total number of server available. This is server 0, server 1, server 2. So you can see that when the first job is arrival at interval 1 actually, so that means we can go and start book the server. So when it will be free, so it will be free because it has 1 2 3 4 5, so we need to have this many load, the request number 1 is received and the load is of 5 actually. I assume that it is 5 milliseconds, something like that. And whenever and how we assigning is already mentioned, that we need to assign I by k whenever there is a job comes. So this is a index is like 0 1 2 3 4, so I by 0 is basically I by 3, which is 3 modulo 3, sorry, it's a modulo 3, so which is 0. So we are going and we are checking, the server 0 is available. Yes, the server 0 is available, so we going and keeping it like this actually, assigning the job to that particular server. Similarly, when the second job comes, we checking, the second I 1 by 1 modulo 3, which is 1, and we check whether the second server 1 is available. Yes, it is available. So we go and see, okay, the starting time of the job is 2, so it will be starting here, and the load is 2, basically it will 2 plus 2, it will be 4, so it will be finished by 4 actually, something like this. Okay, that's the request number 1. Then similarly, we are getting the next load, which is starting time is 3, and it takes 3 milliseconds, or whatever it is actually, the unit which they given. And whenever we look at 3 by 3, the modulo is, here it is 2 actually, okay. 2 modulo 3, which is 2, and we are going and see actually that server number 2 is available. It is available, so we go and assign, so that starting time is 3, and it will go to 3 to 6 actually, which will be R2. Now the load number indexed is 3 is coming. So what is the start time? 4 actually, like, so which server which we need to assign is actually 3 by 3, which is 0, and we go and see actually the 3 is server 0 is available. No, it is not available. So we need to check whether server 1 is available. So when you go and look at it, server 1 is something like, okay, it will finish the job by 4, 4 millisecond or something, the load which is already executing. So we go and see, okay, it's possible to assign to the next server, which is server 1, and we go, the start time of that is 4, and it is all about 3 milliseconds. So it will be like request 3 is going to handle on here actually. Now all are busy. Now we are going to see the next index, which is 4, and we probably need to assign 4 modulo 3, which will be 1. We need to assign that load to server number 1. We see, is it possible we can get and the start time of this server is basically 5, and we go and see here, 5. All this, first we need to check the server number 1 is available. No, it is not available. Then we go and see the server number 2 is available. No, actually. And when it comes to here, there is no other service available. So we need to discard this actually. This basically we need to discard this R4 actually. Okay, so by looking at it, we see that actually, we can have some kind of data structure. Now, how do we need to implement? If you look at it, this one, if you look at it actually, here we are having a load of 1 plus 5, 6. So what does that mean? When it reaches to 6 millisecond, the server 0 is available. So when you look at the load number R1, if you look at it, when the server reaches 4, the time reaches 4, and the server 1 is available. So if you look at it, these kind of scenarios actually, the first request is 6, then the second is 4. Basically we can sort it by end time, so this will be like the end time of each load. When you look at this one, the first load end time is 6, the second load end time is 4, and third load end time is 6, and fourth load this one 8. So if you look at it, which load will be available first, which will be ready to take it, 4. So when you take out 4, then 6. Okay, so like that, if you look at it, so we need something to know which server is available actually. So we need to have a data structure to implement that. Basically the best data structure for handling this case is a priority queue actually. Okay, if we implement this with a min priority queue, we know we can easily we can easily see which is, if you use a min priority queue, we know that when we can look at the top, we go the top. What is top actually? 4. Okay, so 4 means after 4, on 4 actually our one of the server is available actually. So that is one thing which we can think of. We need to use such kind of data structure to implement that. So that will be best. One data structure we already see. Now the second thing is, so how do we know that? Even though if it is 4 is on the data on the priority queue, we don't know actually which server which is free and which server is occupied. All this we never know actually. So we need to add some information into the priority queue. So for that we can check, is it possible we can add something. Okay, so the best thing is actually we need to have a priority queue with a server number actually. So if you put a priority queue, inside the priority queue we can put two information, that end time, and if you put a priority queue with we add one more information like server number. We know that whenever we take out that particular job from the priority queue, we know that which server is free. So that is one thing actually. See another, this is a one data structure which we are going to use. Anyway, this is useful, and we can see whether the which of these servers are free at each interval of time actually. The second thing is actually we need to have some kind of data structure to keep use of server. What are the available number of servers actually, how many servers are available, what is occupied, what is when it is free actually. We need to have some kind of intelligent we need to add into that actually. We can see that how many so in the constraints of this project is, if you look at it, the total number of server is 10 raised to 5 actually. So this many servers are available. So that means, suppose assume that in our case, initially there are 3 servers actually. So what is this actually? There are 3 servers. Initially we occupied this one, occupied, then this is occupied, then 2 is occupied. When there is a 4th job is coming, basically the 3rd index job is coming, we can kick out one of this actually, we can remove this and we can make it available, then once again is occupied, we can make it occupied. So how do we implement and see that, we need to, every time there is a rule that whenever there is a job is available, we need to look at this one, the job index modulo k actually. That's how we need to assign the server. But here if you look at it, if it is not available, if you see that whenever the 4th load, that the index 3, when it comes, 3 by 3 is 0, and when we go there, the 0th load is 0th server is not available actually. So we need to go and next index, next available server we need to find out. So we need to have some kind of data structure we need to use there. And how do we use that? The one approach is we can use bit mask. If you look at it, total 10 raised to 5 means, so we can have some kind of data structure to keep 1 bit to indicate whether 0 means it is not available or 1 means it is available, something like 0 means it is available, 1 means it's already occupied, some kind of intelligence, and we can go and find some way to find that actually, whether whenever if that particular server is find, we can use a mask and we can set that mask whenever it is available. Otherwise we can clear that mask, some kind of intelligence we can use. But the problem with that approach is, it is very difficult to implement in an interview and all, most of the people may not be having good understanding of bit mask. Second option is we can use a vector. So that means we can have a vector of k size, and each position indicates 0 indicates whether the that particular server is available, 1 indicates the server possibility, something like this. The advantage of this is actually when we go, whenever there is a k, I modulo k, which comes, k, we can directly go and check, in that particular array, assume that it is v, we go and check I modulo k if it is available, is equal to 0 or not. If not, we can go then find, then we can go and find which is available, next which is available. We can start a for loop from I modulo k to I less than k, to end, and we can find out, whether which is the next available. If it is not, then we need to roll back and check up to the I by k actually. So this problem with this is actually, this is a linear scanning, so we probably need, when you use this kind of a data structure, we need to use a linear scanning actually. So that is again, it will unnecessarily increase the complexity. So what is the next possible option is we can use a set data structure actually. Okay, So what is this set? Like whenever there is a server is available, we can add how many server available initially into that set. Basically, we go 1, 2, 0, 1, 2. Whenever the server is occupied, we can go and remove that from the set. You understood? Whenever there is a set is, and after that what we can do is a set has a capability to find the next available number, next available, suppose 0 is not available, then we can go to next, next available index, so what we need to do is we need to use a data structure. The set has a capability to do that using lower bound, what is lower bound is basically, suppose if you have 0, 1, 2, 3 and 4, something like that. If you search for a number, suppose if you search for 0, then it will return 0 actually, if it is 1, it will return 1. Assume that if 2 is not present and if you look for 2, so that means 2 is, assume that 2 is not available. That means the 2 is already occupied, the server is occupied. So that time what we do actually, if you look for 2 lower bound, if you use this lower bound capability, which is basically a binary search kind of stuff, it will return 3. That means 2 is not available, the next available server is 3 actually, so that we can use that logic. Assume that if you look for 5 actually, the 5 is not available, so it will reach the end. So basically when it reaches the end, what we can do is we can go roll back to 0th one, because that is already mentioned in the question. So like that, if you look at it, we can implement this problem using that approach actually. So that's what the way which we need to implement. So let me explain you how we need to implement using that. So if you look at this problem, so there are two data structure which we find out. One is basically a priority queue and second is a set. We probably knew, so if you look at this problem, you can see that whenever the server 1 is handling the second load, we need to remove the first load actually. So whenever we adding a load, we need to have another counter, which counter of size k. Whenever there is a load is added into that particular server, we can increment that, so that this will give you this array will give you the maximum number of loads which is handled in a single server actually. So this is another way which we need to implement. So how do we use these three data structure to implement this particular to complete this problem actually? Okay, let me look at it actually. So right now if you look at it, k is equal to 3 and we have an arrival time of 1, 2, 3, 4, 5 and we have a load of 5, 2, 3, 3, 3. So as I mentioned, in the priority queue we are using the end time, and we probably need to use which server which is using actually, so basically which server we will use a server iterator, because we have set, so we can add that iterator. If there is a server is available which we are adding that particular server, we can use that iterator here. The advantage of this is actually whenever it is occupied, we can remove using that iterator the set, and whenever it is available we can add that actually, that's advantage of this using. So let me try to handle this actually. So we have a priority queue. Right now the priority queue is empty, there is nothing is there. So what is the available server, what are the available server? So if either we have 0, 1, 2 available, and what is the count for each server? Basically the count is basically now 0, there is nothing is hand. And so basically what we do actually, we receive a first job, okay, whenever we receive a first job. So the first job arrival time is first 1 and it ends, it has a load of 5 millisecond or whatever the unit which they mention. So that means when you start from 1 and plus 5, so it will take 6. Whenever there is a 6 millisecond or 6 unit it reaches, the first load will be finished. So what we need to do is actually, and as you mentioned, the way which we need to handle is actually, we need to look at it actually. The server, basically this is the index 0, 1, 2, 3, 4, and there are total number of service 0. So 0 modulo 3, which is 0. So we can assign and look at it. We go and look at the server, see that whether the server is available. Yes, it is available. So now we go and change this count to 1 actually, and we put the end time, because it's starting from 1 and it will go to 5, so it will be end time is 6, and we look at the iterator of 0 actually, and now the server 1 is occupied actually, server 0 is occupied. Now the second thing is actually, when it goes to the second index, which is basically the index number 1 actually, the second load, this load starts, and first of all we need to check whether it is that particular server is available. That is 1 by 3, it is available. Okay, so we can directly assign the job there. It starts at 2 and it takes an amount of 2 units. So basically it is like 2 plus 2, it will be available by so now this is when I equal to 0. So basically when I equal to 1 actually, the server will be like so basically the server will be 0 is not available, and 1 we are going to occupy this, and the count which will be 1, and the count number of this is also 1, and the priority queue is now adjusted, because the total number of the amount which is required for this is 2 plus 2, so we will be putting that to the priority queue is a min priority queue, so this will be coming into the top, and the server which is be assigned is 1 actually, and the 6 will be going down. Now if we go to the next server, next load, which is of index 2, 2 by 3, the server which is 2 by 3, 2 modulo 3 is 2, we go and see the 2 is available. Yes, it is available. So basically now 0 is occupied, 1 is occupied, so 2 is now occupied. So all these have load, and what is this actually? So it will be like 3 plus 3, it will be 6, and the server which is assigned is 2. So basically this will go, the priority queue again will be adjusted, but there is no change in the value. The 6 1 will be going to 6 2 will be going to the end. So this is I equal to 1, this is I equal to 0. Now if we go and I equal to 2, I equal to 1, I equal to 2, now I equal to 3. So when you go to I equal to 3, so the server which is required for this executing this job is 3 by 3, it will be 0, and we go and see, we go and see the server number 0 is free or not. No, it is not free. But the interesting thing is, when you look at the priority queue, we can see that there is a job which has an end time which is less than or equal to the next arrival of the next job, 4. Okay, so what we can do is actually, before we are doing anything, we probably need to eject this actually. So basically we go here, and the current status is basically all these jobs are like this, and we see that the start time of the next job is 4, and there is a top of this priority queue has a job which is less than or equal to the start time of this one. So basically what we can do is we can eject this job, and we can, because this job is done, we don't need this to be in the priority queue. So first what we need to do is actually we need to remove this job from this one. So that means our priority queue will become 6-0 and 6-2, and the server number 1 is available right now. But for accommodating this job actually is starting on 4, we need a server of 0 actually. Since the 0 is not available, we look at which is the next available server. That is 1 actually. So we can take this server. Basically the count will increment to 1, and we can see that the total time to execute this job is 7, and which will be like end time for this particular job is 7, and it is assigned to the server number 1 actually. Now that's how the job right now it is running on the service. Now if you go to I equal to 4, which is the 5th job, we see all these jobs are servers are filled, and we have a count of this one, and our priority queue is 60, 62, 60, 62 and 71, and we look at it, what is the start time of this particular job, which is 5. So we can look at our priority queue. Is it possible we can free any of the jobs? No, actually, because the starting time of this one is, which is which is less than this one. Basically we cannot have anything because the job is only free at 6 actually. So because of that we cannot handle that case. So our job is finished. Now after that we need to look at, okay, which server handle the most number of job, which is 1 actually. So that's how we need to implement actually this problem. So we need to return the server number 1 as a result actually. So I assume you guys understood. We can implement this let me implement this one. So if you want to implement, as I mentioned, we need to have a priority queue. And we need to have pair of information. And we also need one more. We are using a min heap. Basically we can use, this is how we need to initialize the end time. So we can call it as a end time of job, something end time jobs actually. So next is like we need to have a set. So there are two ways we can use a map, unordered set and ordered set. So here we need to use an unordered set. The reason is actually we need to know actually which is the next available server in a ordered fashion. Otherwise in unordered set, the problem is actually, suppose if you add suppose we all 3 is occupied, 0, 1, 2, 3, assume that there are 4 servers, then if there is a server 0 is occupied, then the 0 will be coming, and after that when the server 3 is occupied, then 3 will be coming on the top actually, so that it won't, if you look for a next available server, we will be getting a wrong server actually, so to avoid that, if you use an ordered set, we can have a sorted fashion, and we will be able to find the next available servers in a very good fashion actually, as requested by this problem actually. So here we probably need to go and this is available servers. And basically we also we need to initialize this. So what we can do is we can go in I equal to 0, less than k and I plus plus. So here we can go and insert this. So these are the servers available actually. So after that we also need to have a count, you know, I mean we need to know what is the count for each server actually. So we can have something like this one, so that the count will be initialized with the 0 with k number of servers actually. So after that what we need to do is we need to have a for loop, and we need to start with all the jobs which is indexed from 0 to k minus 1, sorry, not k minus 1, it's n minus 1. So go to I less than arrival dot, yeah, this is what actually basically the size of the job, and I plus plus 1. So here, so basically what we need to do is, as you know that whenever there is something is available, you know, like whenever we get a job, and we probably need to check whether the arrival job has a time which is greater than what is currently processing the job in the server. So like that we need to check it, you know, I mean if you look at the top of this one is 4.1. When it comes to this job, you know, like the 4 can be, we can kick it out actually, you know, I mean because it's already finished that particular job. So we need to check that particular case here. So we can have a while loop, and this while loop we can go and see, you know, I mean first of all we need to check whether the end time is empty, not empty actually. If it is empty means we don't need to do anything actually. Okay, if it is not empty and the top dot first is less than or equal to arrival, the first arrival job, which is I, then we know that, okay, interesting, we probably need to job which is ended, job ends, you know, I mean, so which we need to take it out. And what we can do is we can pop out that particular job, we don't need. But as you know that whenever there is a job is popped out, we know that that particular server is free, you know, I mean, so what we need to do is we need to add that server into available server, you know, I mean, so basically we'll go here and insert actually, basically the job ends the second one actually. So that's how we know that. So after that what we need to do here, you know, I mean, so once it is available, we need to find out which is the next available server, you know, I mean for this particular job. So we need to find out from this particular available server, we can see which is free, you know, I mean, so for that what we need to do is we need to go this particular server, we need to use the lower bound actually of, that's how we need to check, you know, we need to initially assign to the job to I modulo kth server. So we go there and assign that here, and we see if it is free. So, yeah, so basically what we can do is we can use an iterator auto it is equal to available 0, and we can see that, so sometimes, if the request number, lower bound, if it is not found, it will go to the end. So if it goes to the end, they already mentioned here in the otherwise assign the request next service, wrapping around this list of server starting from 0 if necessary. So that means what we will do is we go here and we can see that it is equal to available server end actually, So we probably need to find out this too. If it is end, we need to wrap over actually. That's what we need to do. So if it is end, we go and it equal this begin actually. This is what I need to do actually. So now it is we got which is a server for us actually. Now what we need to do is actually we need to assign the job actually, so for that we need to priority queue. We need to so there's a priority queue. Basically our priority queue is end job time. So end times we need to push. So how do we push it? We need to arrival time plus the load and we need to put the server number actually, So after that, what we can do is actually once this is pushed to the priority queue, we need to remove that particular server from this available server. So we go here, we erase this. So now we have everything what we need. And also, whenever we need to count, we need to increment actually. So we go here, it takes this iterator and increment that. That's it. After that, what we can do is so now if you look at it, we are already inputting all these jobs into the priority queue, and we also update the available server based on that. So once ends, we need to find out what's the max count. So for that, what we need to do is we can use a data structure. We can use some of this actually, like we go to this count dot begin. Okay, it's a constant begin, that would be best, right? And count dot end, and we can have another vector, like we need to check this another vector, which is result, and we can look at this actually when int I equal to 0 I less than k, because k number of results are available, I plus plus, look if it is so this max count will give you the max count will give you, the maximum number of job is executed on one particular server. So what we can do is we can go here and put this count. We can easily check it, and whatever it is a max count equivalent, we push that. We push back that that's a server name, so that will give us the answer for this problem. Let's check it. Is a runtime error right now? Lower bound it is equal to this one. Let's debug it. Okay, so I can see that something got oh yeah, so basically this is probably the yes, because yeah, nautical line is stopped at first is less than arrival, so pop insert jobs at second. Okay, it is equal to so end is equal to beginning. So why it is arrival it max element is equal to this one. Why this has why this is taking more time? I plus plus I model. Okay, that's even correct. Okay, let's check, if this is if this available server is empty, we don't need to look at that, we can continue actually. So let's check it. Yes, yes. So basically why it is not ran earlier is because of this particular issue, that whenever there is server is not available, we don't need to run the jobs actually. we can drop that. Actually that needs to be handled. So I can use all the test cases and I can run this, all working, and I can submit this. Is a better solution. It can run up to 88.95 actually. So now the time complexity of this problem. Basically you can see here, you can see that how many jobs are in our priority queue. Basically if there is a job needs to be executed, the server needs to be available. If there is no server available, we cannot execute a job. So that means in the priority queue we'll have number of servers available actually. So that means there is a space required. So the total number of jobs in a priority will be k, order of k actually, right? Because we cannot execute more than one jobs actually. So if it is the time is all, the job is already expired, then it has to be taken out. And if you look at it, this is a priority queue complexity, the space complexity. And if you look at the other complexity is like basically the available server, we are using a set. So there are k number of server. So the set also use similar. So the total space complexity of this problem, and the count also use order of k, because it has same number of k number of counts is possible. So total number of space available is like order of k actually. Now what is the total number of space complexity, runtime complexity? So if you look at an arrival time, suppose if you have n number of jobs, so we need to call this order of n actually, but each time there is worst case, we are deleting some kind of jobs from the priority queue. So on average, assume that every time we delete one job. So for priority queue to removing something and adjusting the heap, it takes log n actually, log k, because there is a k number of jobs there, job k, log k. And to find the lower bound, so if here we are not using a linear search, so here also we using some kind of binary search method. So to find the log, the lower bound, it'll again take log of k, and rest all order of 1. This is order of 1, this is order of 1. And if you look at inserting, pushing a job into priority queue, again it will be like log of k, because there is some kind of heapifying is required. So that means 3 log k, so we can compare all this to log k. So log k order of n in n log k. So that's what this. So this is a space complexity. This is a runtime complexity. I think this is a very good question. So if you guys are wanted to try that, please try and try the similar approach, or something different would be better. Please update that answer to the same link. I'll be able to look at it. Thank you for viewing this, watching this YouTube video. And if you have any questions, please comment me actually. Thank you very much.